So, a generic mechanism for this section. We have a leaving group on our carbonyl. We add a nucleophile to it. What can happen? Well, the nucleophile adds to the carbonyl, breaking the carbon-oxygen double bond. It is not an SN2. Do not draw an SN2. I'll take out 5 points. Don't go there. It adds to the carbonyl. We form the tetrahedral intermediate, and then once we have the tetrahedral intermediate, we can reform the carbonyl, kicking out the leaving group. So this is a nucleophilic addition and then the loss of a leaving group to get us to our product in this reaction. Okay, in almost every mechanism we draw, base catalyzed in this section will be nucleophilic addition, where we break the carbon-oxygen double bond, forming the tetrahedral intermediate, and then reform the carbonyl, kicking out the leaving group. So here we are. We'll continue on with this, and we can prepare acid chlorides. The only way we can make them, since they are the most reactive, they're the one mechanism that's different than all the rest in this section. So we have to turn the OH of the carboxylic acid into a good leaving group, which isn't easy to do. So the only way we can do it is the only good way we can do it is reacting it with thionyl chloride and sodium carbonate, or another weak base like sodium carbonate, to scavenge all the HCl that's formed in the reaction. But the reaction is shown here, and on the next page I do believe we have the mechanism. And what happens in this is, just like every other time, the carbonyl goes and attacks the sulfur. The carbonyl is the nucleophile. It attacks the sulfur. The sulfur has the two chlorines. They're good leaving groups off of it. It also has the double bond at the more electronegative atoms. So that sulfur has a big partial positive charge on it because of that. And it's remember back in Org 1, the carbonyl does the attacking, because when we have something off of the carbonyl and positive charge on that carbonyl oxygen, we can draw resonance structures for that, moving the positive charge back and forth. If we use the OH to go attack it, we cannot resonate that positive charge anywhere, so it's not near as stable. So we attack the sulfur, send the electrons up to the oxygen. In every one of these, form the tetrahedral intermediate and then reform the double bond, kicking out the chloride leaving group. Okay, so now we have the SO double bond. Now the Cl minus can come in, attack the carbon-oxygen double bond, send the double bond up to the oxygen to neutralize the positive charge. And now we have created a very good leaving group off of this carbon right here that was the carbon of the carboxylic acid. So we can send the electrons down from the oxygen of the OH, and then we can kick off the SO2 Cl group, and as we kick it off, we can form a double bond of the sulfur and then kick the chlorine off, and we end up forming sulfur dioxide gas, which bubbles out of solution, and you can't go backwards there. We kicked off a chlorine, so we formed another Cl minus, and then our carbonate base can come grab the extra hydrogen that we had on our carboxylic acid to remove the positive charge off of it to get us to the acid chloride. Okay, now this is a real cool mechanism for making the acid chloride. You have to be careful, just like in the last section, of following along with what can happen. Make sure you get a good leaving group. Always follow all the rules of organic chemistry. Don't skip any steps, and go on from there. Okay, now what can we do to an acid chloride? Well, we can make a carboxylic acid, we can make an ester, we can make an amide, we can make an acid anhydride. Okay, all of these are possible because the chloride is a great leaving group. So all we need to do is have the nucleophile add in, form the tetrahedral intermediate, reform the carbon-oxygen double bond, kick off the leaving group. And then if we're in an acidic solution, we remove the extra hydrogen. If we're in a basic solution, we're done. Okay, so the mechanism for all of these, which is on the next page, are all the same. So be very careful as you're going along that you keep track what can happen and think about it as easy as way of possible. So if we added an alcohol, the alcohol adds to the carbon-oxygen double bond. We break the carbon-oxygen double bond, sending the electrons up on the oxygen to form the tetrahedral intermediate. Now from here, we can do either of the next step. It doesn't matter which order. They're roughly the same energy-wise. Most of the time, people like to reform the carbonyl, kicking off the chloride leaving group to form the protonated ester, and then our base, the pyridine in this example, can come grab the extra hydrogen to form our ester. Okay, and remember, the ester is named by what's off of the oxygen out in front, and then what the carboxylate is of the carboxylic acid it was formed from. So this one is a benzoate because it's from the benzoic acid. So what else can we do with the acid chloride? We can reduce it. If we added lithium aluminum hydride, we can add an H minus N, break the carbon-oxygen double bond to form the O minus, reform the double bond, kicking off our leaving group, and we just formed an aldehyde. And then the aldehyde we can add another equivalent of hydride to it from the LAH to form the alkoxide, and then that alkoxide we can go grab a hydrogen off of to protonate it to make the alcohol. Okay, so this proton at the very end is coming from the water workup or the acid workup in the second step of this. It's not in there with the LAH. Okay, we can do this exact same sort of thing with a Grignard or an alkyl lithium, where the Grignard adds to the carbonyl. We break the double bond O, form the tetrahedral intermediate, reform the carbonyl, kicking off the chlorine. That gives us a ketone now. Exactly the same mechanism in both. It's just the nucleophile is different. And then a second equivalent of the Grignard adds in, breaks the carbon-oxygen double bond to give us the alkoxide. And then it can go grab a hydrogen off of acidic water in the workup to give us the tertiary alcohol. So if we use LAH, we reduce it all the way to the primary alcohol in one step. This just happens all at once. Yeah, it's not multiple steps of LAH. Or we can add an excess of the Grignard, and we can add two equivalents of the alkyl group on there to reduce it down from the acid chloride to the tertiary alcohol. And the mechanism is exactly the same for both of these. The nucleophile adds, form the tetrahedral intermediate, and then kick out the chlorine and add the second equivalent. Okay. In the last section, we talked about this briefly. It ended up being on test 3 from a problem from the textbook. But the Gilman reagent, an alkyl cuprate, can add to the acid chloride. It only adds once, and all it does is whatever's on the cuprate replaces the chloride. So in this example, it'd give us the acetophenone, where we have the methyl adding on there, and then work it up with the water workup. So what can we do with the acid chloride? All sorts of neat things. We can take it, we can make an ester with either the alcohol and pyridine or another base, or we can use the alkoxide. We can use an amine where the amine is either ammonia, a primary amine, a secondary amine, to make the amide. We can reduce it to an alcohol. We can reduce it to a primary alcohol with LAH. We can reduce it to a tertiary alcohol with a Grignard or an alkyl lithium. We can make the acid anhydride. We can reduce it to an aldehyde. Okay, now these two reactions, this one here, reaction A and reaction B, notice the difference in the aluminum hydride, and the one at the bottom, reaction A, we have a trialkoxy aluminum hydride. It's not near as reactive as the lithium aluminum hydride, so it stops at the aldehyde. It doesn't go further than that. We can do the cuprate, where we reduce it to the ketone, and we can just add water to make the carboxylic acid, or the carboxylic acid we can add SOCl2 and a carbonate and make the acid chloride. So I know what you're thinking when you look at this page. There's a lot there. It's really not that much. They all do, except for this reaction right here, they all do roughly the same thing in how what they're doing to the compound. So don't get freaked out that it's a bunch of different reactions. They're all the same going away from the acid chloride. It's just you have to see what changes and what do you need to add to it. Okay, so, and this will come with working a lot of problems out of the book. I did post in D2L some problems to try between now and the fourth test, which is the 2nd of May, I do believe. So be careful, keep up. This section, the last section, was the harder of the last two. In Org 2, as I said, the first test is harder, the second test is easier, the third test is harder, fourth test is easier. Keep working. Some of you are right on the cusp of passing. Keep working. Come in and ask some questions. Send me some emails. However you want to do it to get the help you need so you're successful. So how can we prepare an acid anhydride? We can take the acid chloride and add the carboxylate, a carboxylate, any carboxylate, and the carboxylate negative adds to the carbonyl. We break the CO double bond to form the tetrahedral intermediate, reform the CO double bond, kicking off our leaving group, and there we have the acid anhydride. Okay. As you're going along, look for the similarities in all of these and try to keep it as simple as possible in what you're trying to figure out with them. So what can we do with an acid anhydride? Well, the only thing we can't do with an acid anhydride is turn it directly into an acid chloride. We have to turn it to a carboxylic acid and then add the thionyl chloride and sodium carbonate, and we can turn that into the acid chloride, but we can't do it from the anhydride directly. All the other things work just peachy. Okay, so check this page out, look back 2 pages, and notice as we go down the reactivity of the leaving group, there are slightly fewer things we can do each time we go along.